Okay, in this video, I'm going to be going through what a metal is and why it has some of the properties that it has. So metals are atoms with low effective nuclear charge. What that means then is that they don't have very much hold on their valence electrons. Magnesium's the example we're going to use here. Magnesium has a atomic number of 12, an atomic mass of 24. I'm just rounding using the more common isotope. Again, that means that I have 12 protons and 24 minus 12 neutrons, which is just 12 neutrons. Again, the neutron number doesn't matter, but I just do it because that's what you do. I don't know. And then we're going to assume we're starting with neutral magnesium, so we'll have 2 electrons. And then in the next shell, we'll have 8 electrons. That gets us to a total of 10. And since we're making it neutral, what that means is protons and electrons are equal, which leaves us with 2 more for this outermost shell. Now, to understand how this atom's going to behave from a chemical reactivity standpoint, we're going to take the perspective of the valence electrons, because those are the electrons that are involved in chemical reactions. They're going to look in. And when they look in, instead of seeing 12 protons and 10 separate electrons, they're going to see this entire object as if it's one thing with an effective nuclear charge of 12 protons less 10 electrons, or of positive 2. So positive 2 goes in the middle, and then on the outermost ring, we have our 2 remaining valence electrons. Now, what we remember for effective nuclear charge, the higher it is, the more attractive it is on a scale of +1 to +8. +2 obviously is way down here, and so this is not attractive. What that means then is when this magnesium atom forms bonds with nonmetals, or things with high effective nuclear charge, what's going to happen is these 2 electrons are going to get stolen away. When they're stolen away, what that's going to leave us with is 12 protons, 2 electrons, 10 electrons, and an ion which has a charge of +2, as in 2 less electrons than it had protons. So by losing its electrons, losing its negative electrons, which it did because it's just not attractive enough, then metals form cations, which is just another word for positive ions in compounds. That's assuming they're bonding with other nonmetals. When they exist as metals on their own, or so when they form these metallic bonds, so if we imagine magnesium as the ribbon that we get that we can put in the Bunsen burner and catch on fire, what happens is these +2 ions are surrounded by many, many, many electrons in what we call a metallic bond. All of these electrons have small attractions to these nuclear cores. All electrons have many small attractions to the +2 ions. However, no one attraction between an electron and a +2 is large. So they all sort of give up their electrons, and their electrons still hang out around them, and all those electrons are attracted to all those plus 2s, and all those plus 2s are attracted to all those electrons, and they sort of stabilize each other in that. And all of these interactions are very small, but when you add up the fact that there's many, many, many of them, the overall attraction becomes quite large. So while individual interactions are small, there are many of them, leading to a large overall attraction. This is why, this large overall attraction is why metals have high melting points and why they tend to be hard. But the fact that the individual interactions are small is why they conduct electricity and are bendable. See, it's hard to break this matter up. It's hard to rip it all apart because there's lots and lots of interactions. But it's not hard to get one electron to migrate through the material to a different location. The electrons aren't tied to any specific location. They're free to move. But when you consider all of their small interactions as a whole, there's so many of them that you get to a larger attraction, which makes it hard to melt the overall substance, to take electrons out of the overall substance, or to scratch it. But you can bend it without it breaking. The individual electrons aren't stuck in their individual locations. It conducts electricity and it conducts heat very well. The individual electrons can move around as long as they don't leave the material. So, if a nonmetal comes along and takes the electrons, then the low effective nuclear charge, or the low attraction for the electrons, means that the thing's going to form a cation, a positive ion. If there is no nonmetal to take it, then what they do is they all kick out their electrons and they all share them a little bit. They're not too attracted to any one atom, allowing them to conduct electricity or be bent. On the other hand, when we consider the overall interaction, the lots and lots of things interacting together, it makes it very hard to break up the material as a whole, and it makes the material hard, which leads to the high melting point and the hardness.